Good day, I'm Norman Wildberger. In our last video we had a look at Feri sequences and the relationship with Ford circles, getting at the idea that the rational numbers are not at all uniform as one might think, but rather have a layered structure that one can go deeper and deeper into the more work we do. We're going to continue on with that theme today and introduce another closely related mathematical object going back to the 19th century, to around 1860. This was a joint discovery of a German mathematician, Moritz Stern, and a French clockmaker, Brocault. Stern was the successor of Gauss at Göttingen. They both discovered this particular tree, which is a configuration made up of lots of rational numbers, in fact fractions, they're all positive. And it has remarkable properties and gives us some other insight into the structure of the rational numbers. So we're going to have a look today at the Stern-Brocault tree. Okay, so what we see here is first of all a sort of a starting point 1, 1. Well, it's not quite a starting point. It seems to be coming from these two elements here, and then branching out either to the left or to the right at each point. So it's a binary tree, meaning that as we go down, every element has two below it, one going out to the left and one going out to the right. So for example, if we go left from 1, 1, or 1 over 1, we get a half. Then if we go right, we get 2/3. If we go left again, we get 3/5, 5/8, and so on. If we go down the left-hand side, we get 1/2, 1/3, 1/4, 1/5, 1/6, and so on. The pattern is pretty clear. And if we go down the right-hand side, we get 1, 2, 3, 4, 5, 6, and so on. So we're getting arbitrarily large fractions as well as arbitrarily small fractions close to 0. Okay, so how is this tree constructed? And what are some of its attributes? Well, the key idea is that to go from one layer to the next, we need this idea of a mediant. So basically we're taking medians of the things that have been constructed at a certain stage in order to get the next stage. And just to give you an idea of that, for example, where does this 7/5 come from? Well, the 7/5 is a little bit to the right of 4/3 and it's a little bit to the left of 3/2. And if you take the mediant between these two fractions, and I remind you that means you add the numerators and you add the denominators, then you get 7/5. Similarly, 8/5 is the mediant of 3/2 and 5/3. What about 5/4? Where does it come from? Well, it's the mediant of the term that's closest to it on the right, which is 4/3, and the term that's closest to it above it to the left. So what's above it to the left? 1 over 1. And the mediant of 1 over 1 with 4 over 3 is 5/4. That gives you a rough idea of how we construct the Stern-Brocault tree. And these two objects here are somehow starting points. They are 0 over 1 and 1 over 0. 1 over 0 is not a proper fraction, but for the purposes of this Stern-Brocault tree, we're going to treat it as if it was a fraction. The mediant of this and this is the 1 over 1. So that's sort of how we generate the topmost element in the tree. And to generate ones along the left-hand side, we take the median between any one of these and 0, 1 to get the next one. And to go down the right-hand side, we take the median of this one with this one to get the next one down. The Stern-Brocault tree. So let me now more clearly explain how we build up this Stern-Brocault tree, sort of one layer at a time. We start with the pseudo-fractions 0 over 1 and 1 over 0. Admittedly, this is not a proper fraction, but we're going to treat it as if it was. Then the next stage, we insert the mediant of these two objects, which is 1 over 1, and we put the 1 over 1 in between these two pseudo fractions. And now what we do is we construct more sequences, at each stage adding all the mediants of all adjacent neighboring fractions. So, for example, the next stage, we would take the mediant of these two, which is 1/2, and we would insert it between these two. And we would take the mediant of these two, which is 2 over 1, and insert that between these two. So unlike the process of generating the Féré sequences, we take all mediants between neighboring elements that we have and insert them between the two elements that are creating them. So for example, at the next stage, we take the mediant of these two, which is 1/3, and put it in between these two. Between here and here, we take the mediant, which is 2/3. Between here and here, the mediant is 3/2. It fits there. And between here and here, the mediant is 3 over 1. It fits there. So generating these rows is very straightforward. We just insert all mediants between any two neighboring elements in the sequence. And so, for example, at the next stage, we would end up with this sequence where I've shown you in green the new elements that have been added to the previous sequence. So the 2/5 was added because it was the mediant of 1/3 and 1/2. Gets to be put in between 1/3 and 1/2. So we can continue generating more and more of these sequences. Right, so but how do we actually build that binary tree from these sequences? The rule is that we record these numbers as we generate them, one by one. And what we do is we take any fraction a over b that appears, and below it are the two new fractions introduced to the left and right of AB at the step directly after AB is introduced. So let me try to explain that. So in the previous stage, 2/3 was introduced. Let's have a look at 2/3. That came from the previous sequence. It was actually the mediant of 1/2 and 1 over 1. So suppose we've created the tree up to this level. We've created 2/3 and it's in position. Now after we do 2/3 in the previous row, in this stage here we create the 3/5 and the 3/4, which are the mediants of 2/3 with 1/2 and 2/3 with 1. And so those two new objects that are created, they're created from 2/3, which was the latest new one. They emanate now from 2/3, one to the left, which is smaller, and one to the right, which is bigger. So the 3/5 was actually the mediant of 2/3 with 1/2, and the 3/4 was the mediant of 2/3 with 1 over 1. So at the next stage, if we want to figure out what's going to happen below 3/4, well, at the next stage, after the 3/4 is produced, the next stage will give us a 5/7 median between these two. So that will occur to this side of 3/4, and also a 4/5 to this side of 3/4. That's what we put below 3/4 at the next stage. And below 3/5 at the next stage, well, we would get the mediant 5/8 on this side and 4/7 on this side. So let's see how it goes in practice. Let's actually generate the first few rows of this Stern-Brokow tree. So we're starting with our pseudo fractions 1 over 0 and 0 over 1, and their mediant is 1 over 1. All right, so the next row means that we have to find the mediant of these two, and we'll put it halfway between them, below this one. The mediant is 1 over 2. And the mediant between these two we'll put halfway, and it's 2 over 1. And these are both less than this one. Okay, good. Now below 1/2, Well, in the sequence that we've got so far, 0 over 1 and 1/2 are neighbors, so their median will be 1/3, which we'll put here, and the median between these two is 2/3, which we'll put here. The median between these two is 3/2, which we'll put here, and the median between these two is 3 over 1, which we'll put here. Okay, now at the next stage, each one of these is going to have 2 children. So this one of its neighbors in the sequence, as we sort of read from left to right, is this one here, and its other neighbor is this one here. So we have to take the median between these two and the median between these two, and those are the children of 1/3. So the median here is 1/4, and the median here is 2/5. How about this one's children? Well, with this one here, which is its leftmost neighbor in the sequence, we get a median of 3/5. And with this one and this one, the median is 3/4. And then also this one will have 2 children, and this one will have 2 children. And it's not too hard to see that everything is going to be reciprocated over here. We're going to get the reciprocals of the ones that we got here. Let's check that. So median 1, 1, 3/2 will be 4/3. That's the reciprocal of that one. The median between these two is 5/3. That's the reciprocal of that one. Here the median is 5/2, which is the reciprocal of that one. And here, the median is 4 over 1, which is the reciprocal of this one. Okay, so now as a complete sequence, we could read from left to right. This one, then this one, then this one, then this one, this one, this one, this one, this one, this one, then this one, this one, this one, this one, this one, this one, and this one. They're staggered up and down, but that's still the order in which they appear. All right, let's see if we do one more. Children here, 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 and here. And I'll just do the first half and then take reciprocals. So median between these two is 1/5. Between these ones is 2/7. These ones is 3/8. Between these ones is 3/7. And then between these two, because after this one, as we move left to right, go from here to here. So 4 plus 7 over there. Median here is 5/8. Median here is 5/7. The median here is 4/5. And here we should get the reciprocals. So 5/4, 7/5, 8/5, 7/4, 7/3, 8/3, 7/2, and 5 over 1. So that's how we generate the Stern-Brokow tree. As a binary tree, we think of this as the top node, although there are these sort of pseudo nodes above it. But as a binary tree, this is the apex, and at every stage we have 2 branches coming out. At every stage, all the numbers that we've created form well, there's first of all a row, but all of them in the entirety can still be thought of as a linear sequence. We're now going to have a look at some properties of the Stern-Brokow tree. I'm going to list these properties, and I'm going to leave them mostly to you as some exercises to try to prove or understand why these properties are true. Some of them are rather subtle and require some serious thinking to see why they are true. So this is a great research project. I think generally the Sternbrokoe tree, while well appreciated in certain circles, is not as widely appreciated as it ought to be, which probably means there's quite a lot of more interesting properties that have not yet been discovered. So maybe you'll be able to discover some yourself. The most interesting property, I guess, that pops out at one is this one. That if we exclude the pseudo-fractions that we started with, that every fraction, in other words, every rational number greater than 0, appears exactly once in the Sternbrokoe tree and in reduced form. It's a remarkable and beautiful property of this tree. Another important but somewhat more obvious property is that the order, the numerical order, is respected by the horizontal positions. So in other words, larger fractions appear to the right of smaller ones. Another property that we've already mentioned is that each row of the tree is symmetrical with respect to taking reciprocals. So for example, this was one of the rows that we created, and we already noticed things like 1/4 here is reflected with the 4/1 on this side. So there's a symmetry around the center given by reciprocation, just interchanging numerator and denominators. For the next few properties, we need a definition. Let us say that two fractions r equals a over b and s equals c over d in reduced form are adjacent precisely when AD minus BC equals either plus or minus 1. In that case, we will say that the two fractions r and s are adjacent fractions. So we're introducing an idea of adjacent fractions. Notice that this is pretty close to the rule for equality of fractions. If this expression happened to be 0, then we would know that these two fractions or rational numbers were in fact identical. So adjacent fractions are ones which are not identical, but which are pretty well as close to being identical as possible, in the sense that this quantity AD minus BC is as close as possible to 0 without actually being 0. Alright, so our next property is this one, that any two neighbors in the Sternbrokoe tree are adjacent. And what I mean by neighbor now is that they are connected by a bond or an edge of the tree. So for example, this is part of the tree. There's 1/2 and one of its children is 2/3. So there's a bond or an edge between 1/2 and 2/3. And this property is saying that these guys are actually adjacent fractions. We can check that by taking 1 times 3 minus 2 times 2. That's minus 1. So those guys are indeed adjacent. And the children of 2/3 are 3/5 and 3/4, and they are also both adjacent to 2/3. Because 2 over 5 minus 3 over 3 is 1, then because 2 over 4 minus 3 over 3 is minus 1. For our next property, we make another definition or a notion. We observe that when we look at the tree, below every number that appears in the tree, there is a region in the plane carved out. Namely, it's the region, this sort of connected region, that's directly below, if we imagine sort of joining all the dots. It's like a fence. Then that fence would prevent us from going from here to here, but we could go down the fence actually quite as far as we wanted to. So we'll call this region here, which only depends on 2/3, we're going to call it R sub 2/3. So this is the region controlled by 2/3, if you like. So every node or every point or every number in the Sternbrokoe tree gives a region in the plane, which is cut out by the sort of successive children that you get by going left and then right and then right and then right and so on, or right and then left and left and left and left and left and so on. So this is our notation. If we have a fraction s, then the region corresponding to it is R sub s. And now another property is that every fraction r on the boundary of R sub s is adjacent to s. So in other words, if we look at 2/3 here and look at all the fractions which are on the boundary of R sub 2/3, which includes not just the children but also some of their children and some of their children and so on, that all these numbers here are all adjacent to 2/3. So for example, 2/3 is adjacent to 5/7. What does that mean? It means that 2 times 7 minus 3 times 5 is, in this case, minus 1. Or 2/3 is adjacent to 7/10 because 2 times 10 minus 3 times 7 is also minus 1. Same thing with 7/11. 2 times 11 minus 3 times 7 is plus 1. So there's as many adjacent fractions that you like. Just keep going down here on the boundary of R sub 2/3 and you get more and more fractions which are adjacent to 2/3. So they'll be getting bigger and bigger as we keep going down. Our next property concerns a certain notion of simplicity of a fraction. So suppose that R equals A over B is a fraction in reduced form. Let's define the simplicity of R to be the number L of R, which is 1 over A times B. So we take the product of the numerator and the denominator, we take the reciprocal of that, and we call that the simplicity of the rational number. So if the numerator and denominator are big, then A over B is big, and 1 over A over B will be a very small number, close to 0, which means that its simplicity is very small. It does not have a lot of simplicity, which might suggest that we should call A times B the complexity, which makes a lot of sense. But we're only going to be needing the simplicity for this next property, which is that the sum of the simplicities along any row of the Stern-Brokow tree is 1. So here's a row of the Stern-Brokow tree. 1/3, 2/3, 3/2, 3/1, just when we read along horizontally along one of the rows. The simplicity of this is 1 over 1 times 3, so 1/3. Simplicity of this one is 1 over 6, because 2 times 3 is 6. Similarly, this is 1/6, this is 1/3, and they add up to 1. This result has been attributed by Alex Bogomolny to Pierre Lamothe, a Canadian musical theorist. I think this is lovely. That I think Pierre discovered this in the context of some investigations with music theory. And I should say that Alex Bogomolny is rather famous for his wonderful website called Cut the Knot. And if you haven't been to this, I suggest that you have a look and check it out. It's a great compilation of all kinds of interesting mathematics, in particular lots of lovely geometry, which Alexander has exhibited very clearly with lots of beautiful applets. Okay, so you can spend hours and hours or days and days going through this, this site. Lots of good stuff there. And if Pierre ever watches one of these videos, I wouldn't mind him telling us how he stumbled upon this thing and what the relationship with musical theory is. I think that's a very interesting issue. Okay, another property is that if we start from 1, 1, and let's say we happen to move left and then right and then left and right and left, so denoted by L, R, L, R, L, and down the tree, the fractions that appear are these ones here. 1 over 1, 1/2, 2/3, 3/5, 5/8, 8/13, 13/21. And we see that these are the Fibonacci numbers. And we might call this a Fibonacci path. On the first slide of this lecture, you saw that path in red, sort of zigzagging down. Of course, there's another one, sort of the reciprocal path. If we started right, left, right, left, right, left, then we would get a similar kind of thing, but with all the reciprocals. We could call that the other Fibonacci path. Now, it seems to me it is possible, or perhaps very likely, that this particular sequence down the tree has some special interesting properties. In particular, just a very bit of investigation suggests that this sequence contains the numbers along every row which are maximum for the sum of the numerator and denominator, as well as the product of the numerator and denominator. This being the complexity, perhaps, of the rational number in keeping with the definition of simplicity. So maybe some of you can check this out for me and see if this is true. If you go down further in this tree, is it still true that if you go along any row, that the ones with a maximum sum of numerator and denominator, or maximum product of numerator and denominator, are always in this Fibonacci path, or its reciprocal? And can you prove it if it's true? Our last property is a small observation I've made. It's no doubt well known by the people who've looked a lot at Stern-Brokow tree. If r equals a over b is in reduced form, suppose we define the total of r to be, say, t of r, which is the sum of a and b. So a little bit different from the complexity. We'll call this the total of the fraction. Then the sum of the totals along any row is twice a power of 3. More specifically, the sum for the nth row, that is the row beginning with 1 over n, is 2 times 3 to the n minus 1. So for example, this row here, the sum of the totals is 4 plus 5 plus 5 plus 4, which is 18, which is 2 times 3 squared. So as an exercise, you might like to prove this. And a hint, you could use induction. And a sort of related kind of thing, you could prove that the sum of the first half of any row, that is, if you just add up the fractions themselves, in a simple-minded way, then the sum of the first half of any row is a power of 2. And you might also try to figure out what is the sum of the second half of any row. Now, there are probably a lot more properties that can be established and discovered, and I think it's sort of a fun exercise if you have some interest in number theory and patterns and arithmetic. The Stern-Brokow tree is understudied. There are lots of beautiful things that are probably waiting to be discovered about this object. And now let's connect the Stern-Brokow tree to the Ford circles that we had a look at in our last video, which is also the topic of Math Foundations 14. So here's a picture of part of the Ford circles. There's 0, 1, 2, 3, and so on. Here's the x-axis with our rational numbers spread out around here. Here's the y-axis with a half here and 1 here. And here are the biggest Ford circles, one above every integer. And for convenience, we're going to kind of rub out this 0, 1. We're going to ignore it. And sort of start out with the circle above the number 1. So its point here is 1.5. And the way we get the Stern-Brokow tree from this is we're going to move either left or right from the center of one circle to the center of an adjacent touching circle. And what we're going to do is, at each stage, we're going to move left or right to the biggest tangential circle of lesser or equal diameter. So starting here, if we move right, well, then we move to this equal size circle. We go from here to here. And then another right would go from here to here, and so on. Moving left, well, this one here we've rubbed out, so it's not there. So we have to go down here to this one here. All right, so this one here is the circle above a half. If we go left from this one, we're not going to go back to this one. We're always going to go to some new circle that we haven't gone before because we want a tree. So we're going to go down to the next biggest circle that we haven't gone to, which is touching this one, which is to the left, which is this one here. So left would go there. From here, left would go there. And then from this point, left would take us to this circle here, which is touching to the left and the next biggest one. Right would take us down here to the next biggest one. And then from here, left to this one, right to this one. From here, left to this one, right to this one. So at this stage, there's always two circles that are touching, which are the biggest, and we're moving to those biggest ones which are touching directly that we haven't gone to before. And please check out that we recover the Sternbrokow tree this way. So this is really the number 1. This is the number half because it's above a half. Over here is 2/3. Over here is 1/3. Here is 1/4, 2/5, and so on. So the Sternbrokow tree is very nicely contained in these forward circles. This also, by the way, allows us to connect the Sternbrokow tree with the Feri sequences. Because we saw that the Feri sequences are what we get when we go down a certain level and then start going across and sort of recording all of the circles that we meet as we go from 0 to 1 at a certain level. So you see there's some interaction between the Feri sequences and the Sternbrokow tree, but it's a little bit subtle because the Sternbrokow tree is kind of going down and sort of crosses any Feri sequence path. So all these notions kind of come together pleasantly, I think, in this picture with the forward circles, illustrating again that there's a very natural and interesting deep structure here of the rational numbers. So coming back once more to the Sternbrokow tree, let's have another look at it. We've talked quite a lot about some of its interesting properties, but there's a couple of interesting questions that we haven't addressed yet. One of them is, how do we generate a part of this tree if we start at some particular rational number? Suppose we just start at 4/3 and we ask, what are the children of it? How do we get 5/4 and 7/5 from 4/3? Of course, it's not hard if we already know that above 4/3 is 3/2 and above 4/3 over here is 1/1. But suppose we just start with 4/3 itself. How do we go down? That's a reasonably interesting question, which is not so obvious, and maybe you'd like to think about that. It's an interesting little challenge. There's something else that we need to address. There's another problem that we've skirted here. Can you think what it is? So this is a course in the foundations of mathematics. We want to set things up in exactly the right way. We don't want to leave any little blemishes anywhere on the landscape. Our opinion is that if we do mathematics right, it all makes 100% sense. Not 99%, not 99.5%. It makes 100% sense if you do things the right way. And if it doesn't make 100% sense, if there's even a little bit of problematic aspect to your theory, it's because you have not understood your theory correctly yet. So what is the problem? There is a nagging issue here that I hope is bothering some of you. The nagging issue is this thing. What is 1/0? We've used 1/0 to generate part of this tree. We've used 1/0, for example, to take the median of this one with this to get 3/1. And then the median of this with this to get 4/1, and so on. This is not a fraction. This is some kind of strange object. What's it doing here? No, we shouldn't just shake our heads and say, well, that's just the way it is. You know, mathematics has quirks. No, we should try to understand what's going on here. It means that our understanding is not yet at the level where we completely are in control of things. So next time we're going to have a look at this issue, and it's going to open up another aspect of this deep structure of rational numbers. We're going to talk about a matrix formulation of the Stern-Brokow tree, and then I'm going to introduce a new theory called wedge theory. Okay, so wedge theory is very close to the Stern-Brokow tree, but there are some rather strange, very narrow kind of objects that appear. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.